Meet Maya. She's sitting at her kitchen table, staring at a coin in her hand. Her little brother just bet her that if she flips it 10 times, she'll get exactly 5 heads. Maya thinks he's right. After all, it's a 50-50 chance, isn't it? But when she starts flipping, something surprising happens. That's what today's lesson is all about: experimental versus theoretical probability. Let's find out what Maya discovers. So Maya asks herself, before I even flip this coin, what does math say should happen? That's theoretical probability. It's what we predict will happen based on perfect, fair conditions. Here's the formula. Probability equals the number of favorable outcomes divided by the total number of possible outcomes. For a coin, there's 1 heads out of 2 possible sides. So the theoretical probability of heads is 1 out of 2, or 1/2. Simple and clean. That's the math prediction. Now here's where it gets really interesting. Maya actually flips the coin. She doesn't just predict, she tests it. That's experimental probability. It's the probability you calculate after running a real experiment. The formula looks similar. Experimental probability equals the number of times the event happened divided by the total number of trials. If Maya flips 10 times and gets 3 heads, her experimental probability of heads is 3 out of 10. Real results from a real experiment. That's the key difference. Let's put these two side by side so the difference really clicks. Theoretical probability lives in the perfect math world. Everything is fair and balanced. Experimental probability lives in the real world, where results can surprise you. Here's the big secret. The more trials you run, the closer your experimental probability gets to the theoretical value. 10 flips might give you 3 heads, but flip that coin 1,000 times, you'll land very close to 500 heads. More trials means more accuracy. Remember that. It's the golden rule of probability. Maya decides to level up her experiment. Instead of just flipping a coin, she grabs a standard 6-sided die. She wants to find the probability of rolling a 4. First, theoretical probability. There's 1 4 on the die and 6 total sides, so the theoretical probability is 1/6. Then she rolls the die 20 times and records every result carefully in a table. This is how real scientists and mathematicians work. Set up your experiment, run your trials, and track everything. Maya is basically doing math science right now. Here's a super useful skill, converting probability to a percent. You just multiply by 100, so 1/2 becomes 50%. 1/6 becomes approximately 16.7%. This makes it really easy to compare theoretical and experimental probability side by side. If Maya's experimental result after 20 rolls is rolling a 4 exactly 4 times, her experimental probability is 4 divided by 20, which equals 1/5, or 20%. Compare that to the theoretical 16.7%. Pretty close. Percents are your best friend when analyzing probability results. Let's work through Maya's original coin flip experiment. She flips a coin 10 times and gets heads on flips 1, 3, 5, 7, and 9. That's 5 heads total. First, the theoretical probability of heads. 1 favorable outcome divided by 2 total outcomes equals 1/2, or 50%. Now the experimental probability. Maya got heads 5 times out of 10 flips. 5 divided by 10 equals 1/2, which is also 50%. Now let's try Maya's die experiment. She rolls a 6-sided die 20 times and records her results. She rolls a 4 exactly 3 times. Let's calculate both probabilities. Theoretical probability of rolling a 4, 1 favorable outcome divided by 6 total sides equals 1/6, which is approximately 16.7%. Experimental probability, Maya rolled a 4 3 times out of 20 total rolls. 3 divided by 20 equals 0.15, which is 15%. The theoretical says 16.7%, and the experimental gives us 15%. These are close, but not identical, and that's completely normal. Let's try one more example. Imagine a spinner divided into 4 equal sections, colored red, blue, green, and yellow. What's the theoretical probability of landing on red? 1 section out of 4 total equals 1/4, or 25%. Now Priya spins it 40 times and lands on red 12 times. Her experimental probability is 12 divided by 40. Let's simplify that. Both 12 and 40 are divisible by 4, giving us 3 over 10, which equals 0.30, or 30%. Theoretical is 25%, experimental is 30%. A small difference, but that's how probability works in the real world. Here's the most important idea in all of probability. Maya flips a coin just 10 times and gets 3 heads. That's an experimental probability of 3/10, or 30%. Then she flips it 100 times and gets 47 heads. Experimental probability of 47 hundredths, or 47%. Finally, she flips it 1,000 times and gets 503 heads. That's 503 divided by 1,000, which equals 0.503, or 50.3%. Look at that trend. As the number of trials increases, the experimental probability gets closer and closer to the theoretical value of 50. One more real-world example. A bag contains 3 red marbles and 7 blue marbles, 10 total. What's the theoretical probability of pulling out a red marble? 3 red out of 10 total gives us 3/10, which equals 0.30, or 30%. Now Jordan reaches in and pulls a marble 20 times, replacing it each time. He gets red 8 times. His experimental probability is 8 divided by 20. 8 divided by 20 equals 0.40, or 40%. Theoretical is 30%, experimental is 40%. The gap is larger here, but that's because we only ran 20 trials. More trials would bring them closer together. Last example. Maya draws a card from a standard 52-card deck. She wants to find the probability of drawing a heart. There are 13 hearts in a deck of 52 cards. Theoretical probability, 13 divided by 52 simplifies to 1/4, which equals 0.25, or 25%. Equals 0.35, or 35%. Theoretical is 25%, experimental is 35%. With only 20 draws, this gap is expected, and with more draws, they'd get much closer to matching. Before we wrap up, let's talk about mistakes students often make. Number 1, assuming experimental probability will always equal theoretical probability. It won't, especially with small samples. Number 2, thinking something is broken or wrong when results don't match predictions. That's just how randomness works. Number 3, using too few trials to draw conclusions. 10 flips of a coin is not enough to say the coin is unfair. Always remember, both types of probability are useful tools, and neither one is wrong. Remember when Maya was staring at that coin, wondering if her brother was right? Now she knows exactly how to answer him. Theoretical probability tells us what math predicts. Experimental probability shows what actually happens. And the more times you test it, the closer those two values get. That's the law of large numbers. Whether you're flipping coins, rolling dice, spinning spinners, or drawing cards, you now have the tools to calculate both types of probability like a pro. From confused to confident. That's the probability journey. You've absolutely